Hey friends, it is Ben once again, and I am recording a video that is set for Thursday, April 27th, I think it is. The assignment that we're looking at is dealing with multiple samples in some senses. I'm going to go directly to the notebook. There are only 4 problems to work out here, but I feel like the explanation of what's going on is going to be more significant than than anything else with it. Okay. So here we go, share screen. And yeah, there it is. All right. And so the thing that we're looking at here is really the notion of doing a hypothesis test about 2 samples being different. So we'll start off saying something about the 2 sample z-test. I don't actually have you doing anything with the 2 sample z-test, but rather just reading through the example and seeing what's happening with it. So the idea in either one of these is that you have 2 samples that are from a normal population, and your null hypothesis is that they are two populations with the same mean. And then your alternate hypothesis is that they're a different mean, that it's not equal, or one is less or one is greater. Okay. And all of the actual work that you would do about calculation is just taken care of for you in this. All right. So the example that I make reference to here in the writing is if you were testing the efficacy of a drug, you would often have 2 different samples. One would be a treatment group and one would be a control group. And ideally, you do double-blind studies and all that good stuff. So you'd avoid as much bias as you could, okay? But so the notion with the z-test that we talk about is that you know what the standard deviation is for the 2 populations. And it's going to be sigma 1 and sigma 2, and it's figured into the calculations that you do, okay? But then what I work through here is, here's an example that I found online that's doing that sort of thing. And it purports to be a z-test, but then with the actual calculation, it does not ask you for a sigma 1 or a sigma 2. So z-tests have to be given the population standard deviation. And this isn't. So when I went and dug into the documentation for the z-test that I found, turns out it's a t-test. So if it's a t-test, we'll just do a t-test, okay? Because that's what's built in and that's what you in general will do. Because realistically, you never know those population standard deviations. You're always having to do a calculation of the sample standard deviation. And so since all that is built in and taken care of for you, we're just going to do t-test stuff, okay? But you can see an example there of doing z-test. If you take a stat class at some point and they talk about a z-test, humor the professor, even if it's me, and go along with it. But nobody does, from what I can tell, nobody does actual z-tests in what they're doing unless they're doing a t-test and calling it a z-test, like Python apparently does. So, okay, so working through that, the example that they had came up with a p-value that was less than 0.05. And so you would have statistically significant samples, but again, it's doing it with a t-test. So, yeah. So we're going to look here at another example with a 2-sample t-test that's labeled t-test, and it's from a package called, I would pronounce that as penguin. Maybe they want you to pronounce it as penguin. but I'd say Penguin. In any case, it turned out that that package was something I did not have installed. So this is something worthwhile for you to see when you have a package that you're working from, or that you're supposed to try to work from, that isn't installed. The way you get it installed is with this trick here. You say exclamation point. Actual computer programmers refer to that as the bang character. So they would say bang pip install Penguin. Okay. And if your Jupyter Notebook installation has access to the Penguin package, that will get it installed for you. As you can see on my having done it, it put out a bunch of text to say it was doing it. But once it's installed, it should be installed forever, I think. I don't know that for sure. Yeah, I don't know that for sure. So keep in mind that when you use it again, you need to check and see whether it stays installed on whatever your instance is that you've got for doing Jupyter Notebooks. Okay. Let me know what you find out. So in any case here, then the example that I'm working from then came from this website here. And we're going to use something from stats models, stats, weight stats called t-test underscore ind. That is to say, it's a t-test for independent samples. Okay. And yeah, so t-test for independent samples. And we'll come back and say something more about that here in a minute. But several of the examples that I've looked at ended up doing things from stats models. So this is apparently a package that gets used. Okay. We're also importing NumPy and then this Penguin package. Okay. And so anything that has that prefix of PG in it in this code is coming from the Penguin package. But the thing that I did here was to have two sets of data. I have no idea what the data is. It just seems to be a bunch of numbers. So, you know, this isn't great in that sense. So, sorry. But the thing we do is to set them up as NumPy arrays. That's why it says NP array at the beginning of it. And then if you just use a square bracket, and then make your list with the commas in there. Okay, so that's going to make you a NumPy array. I believe in this case here, sorry, checking something real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And one of them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this one has 10 in each sample. If they are independent samples, you don't need them to have the same number of things in them. If they are dependent samples, then they're supposed to have the same number of entries. I did not experiment around with this to check and make sure that it wouldn't cause problems having different length samples, but from the technical perspective, it's supposed to not need to have the same length. Although every example in every textbook I've ever dealt with always gave samples that were the same size. It shouldn't be necessary. So, all right. Anyway, though, as we're going here, we have just established variables for the two sets of data. And then we have our result read out by PG, that's the Penguin package, t-test, so the name of it is just t-test. And you tell it the name of your first data group, this name of your second data group, and this part of correction equals true. I don't know what that does. So leave it in because it was in the example that I saw. Now these two pieces down here, alternative equals two-sided. If you don't put this in, it will assume alternative equals two-sided. I put it in so you would see how to change it. So now you can put in I think it's greater or less. It might have been larger or smaller. Take a look, because I will have more details about it in the writing. But that determines whether your H naught says not equal to or greater or less. Okay. Then this part here where it says paired equals false, that means we're talking about an independent samples. If they were paired, like before and after, or if you were comparing two things that were obviously supposed to go together, then you would want to say paired equals true. Okay. But then this prints the result here. And notice the way that it organized. I liked the organization on this better than what I saw on other things. So it tells you the t-value, which probably doesn't mean a lot to you, but there's certain things where people need to know what the test statistic is. So that's the t-value if it's needed. Your degrees of freedom. This does not make any sense to me. The degrees of freedom on this ought to be either 9, because you've got 9 pairs, or it would be 19, because you've got 20 things in total. But this 14.3 something comes from some wild formula. So if this ever comes up and you have to quote a degree of freedom, you've got it here, but I don't know what really to do with it. It tells you about what the alternative was, and it gives you the p-value. Also, it gives you a confidence interval. There is, if you go to, if you go to the website for this statsmodels.stats.weightstats, and you look up the t-test, it tells you how to set the level of confidence for confidence intervals there. But you have to kind of dig down and find it. We're not really doing confidence interval stuff for this, so I'm not going to try to talk to you too much about it, but you can get that. They also on that website talked about the Cohen D statistic, and it tells you something about how much of a difference that you actually see between things. Again, I don't know a lot to tell you about that. But so this BF10, I don't know about, and this power that comes out of it. If you take a research methods course in a particular subject, they will talk to you about the power of tests. I don't know a lot to say about them. Okay, what we're essentially going for here is this p-value. As you can see, that p-value is 0.52, and some other numbers. It's nowhere close to 0.05. This is very much larger than 0.05. That means we do not have significant evidence at all. We need to have the p-value, the probability of being wrong, to be less than 5% in order to actually have something significant come out here. So we don't. But this shows you how to run the test. And so here with problem 1 that I'm asking you to do, you'll see basically what to do. So the first thing I'm going to ask you to do is to read in the vehicles.csv data like you've done on other examples, and then pick out a make and model of car. I might pick the Kia Soul because I drive one of those. But if you want to get a Chrysler Town and Country, or the Infiniti Q30, I think that's the model of one of the Infiniti cars. But pick out something that and then get the data that you've got for that, and read out the highway mileage into a NumPy array, and read out the city mileage into a NumPy array. Okay. And so now you're going to have 2 paired things. Paired because you'll have the highway mileage and the city mileage for the same cars, right? Then what I want you to do about that is to test whether the difference is I didn't mean to do that. Why do I keep doing that? Test whether the difference is statistically significant. I used bad phrasing for that. I shouldn't say test whether the difference is statistically significant, because that implies that your H sub A, your alternate hypothesis, is mu1 not equal mu2, okay? Because you know almost always that highway mileage is more than city mileage, you should instead be testing whether mu1 is greater than mu2. Or if you reversed which one's 1 and 2, it might be less, okay? So I want you to make that change as well. And then in your code cell that you've got there, I need to put you a code cell in here. And I have messed it up where that's not easy to do. Okay, so in that code cell there, after you've read those things in and you test for that, that means you're going to set alternative to either less than or greater than, depending on what you've decided. If you get a p-value that's more than 50%, more than 0.5, that means that you should have done the opposite. If you did less and got 0.9 or something, you should have done greater, okay? Anyway, but also on this, paired is going to be equal to true for this example because you've got the same car and it's highway and city miles, okay? So work that out. Once you've got a p-value coming out of that, make the determination whether you've got strong evidence or not, whether you've got a statistically significant result, and then write a text cell that says that, okay? And if you end up not getting a strong result, then you didn't get a strong result. It's okay. So that's what we're looking for problem 1. Then heading into problem 2 here, we're going to talk about the 2 proportion z-test. So the 2 proportion z-test is talking about 2 fractions. We had the example the other day where I wanted you to determine whether or not the poll results said that a candidate was going to get more than 50% of the vote, right? And I had you do quite a bit of playing around with that. But now we're talking about you've got 2 fractions that you're comparing, either comparing to see if they're not equal or one is greater than the other. So if you were talking about voting again, this would be this sort of example of having an election where you could win by just getting a plurality. I don't know if that's a word everybody uses, but plurality just means the candidate who got the most votes, right? So if you have a presidential election that ends up with nobody getting more than 50%, I believe, I do not know what happens with the House of Representatives on that, okay? And then state by state, it's determined whether a plurality is good enough or if you have to have runoff elections, okay? So in any case here, another thing that you might do this with is if you have something like 2 manufacturing processes and one of them ends up having flaws show up at a certain rate and the other one has it show up at a different rate, and then you have to see if they're statistically different, okay? So that's the kind of thing that's going on in this example here, although it's not really said in the example that I found. So in this example here, we are again taking something from stats models and we're doing the proportions z-test. And this time it actually will be a z-test because certain things going on with the proportions actually figures out what the sigma is behind the scenes, So in this case, we've got 5 out of 83 and 12 out of 99. We're trying to determine whether those two proportions are statistically significantly different. All right. So with regard to that, we put the counts, these are the numerators of our fractions. And it looks like for some reason they like to call that counts. I called it X, but you can call it counts if you want to. And then for N, that's really the denominators of our fractions. And they like to call that N observed. And I kept reading it as knobs. And I was like, why are they spelling knobs that way? That's weird, but it's N observed. Okay. So then for this, you hand it to the proportion z-test. You just tell it the X and the N and have them as these arrays with two entries in them, and tell it the alternative is two-sided or greater or less, depending on what you're doing, right? But tell that to pass things back to stat, comma, p-value, okay? They don't have to be named that, but I named them that. Alternately, you can pass them to a single variable and then have it read out the p-value. I have some examples doing that and some examples doing it the other way so that you can see both examples. I'm sorry if that's confusing, but you need to realize that computers, programming stuff, different packages are not always going to be consistent with each other. So it's good to know both ways. Anyhow, though, the p-value that came out of this was 0.159. That says that 5 out of 83 and 12 out of 89 is not statistically significant at that 0.05 level. Okay. So, so the example I want you all to do, problem number 2, I went and got the numbers for just from a website of the Republican frontrunners. And when you see that, you can see that Donald is way ahead of DeSantis. But, you know, maybe we can look at some of the other people that are in the race because, you know, there's other folks running. And so it came out of 3,600. Oh, I did it again. 3,640 voters. And it said that 7% favored Mike Pence and 3% favored Nikki Haley. Now, it didn't have very precise things. It didn't go into decimals of a percent or anything. So what I want you to do is to just take 7% of 3,640, whatever that turns out to be, and that will be one of your X's, one of your counts. And then 3% of 3,640, and that'll be your other count. So it was 7% for Pence and 3% for Haley. Okay. But get those two numbers, and both of them are going to be out of 3,640. So your N values array will just have 3,640, 3,640. Okay. And then test whether that's a significant evidence of a difference. Remember, difference is the not equal to, and that'll be two-sided. Okay. And see what you get. And then, as always, put in a block of text and tell me, you know, what the actual results were. I need you to understand my big goal in all this is to see whether you understand what it is you're doing, not just, you know, typing and changing code, but seeing what it actually means. Okay. All right. So hopefully that will give an illustration of that sort of thing. I'll point to something later where this is where this actually makes sense to be doing with data science stuff. It seems like it's very much just doing statistics, but it's a data science thing. So then one of our other big things is talking about analysis of variance. And the example in this would be if you've got a bunch of different treatments that you're trying, maybe in some sort of medical trials where you're looking at different treatments for the same illness and comparing to see if one of them is better, or if, some of them are better, or whatever. And so your null hypothesis on ANOVA testing is always going to be that all of the means are the same. And the alternate hypothesis is going to be that at least one is different. And the example that I found online that had one of these worked out turned out to get, out of 5 samples, 2 of them were significantly higher than the other 3. Okay, so let's look at how that goes. So the actual thing that we're working out here in the code, we're pulling this from Skippy stats, and we're doing, it says F one way. The one way is for the ANOVA testing. The F is because it's an F statistic. It's just another one of these mini distributions. But what it's actually going to do is to calculate for each of your samples what the standard deviations are. And then it calculates, if you put all the samples together, what the standard deviation would be from that one big thing. And then it takes a look at how much variation is within the samples themselves and how much is a variation between the samples. The F statistic that it gets really large if there is a lot of variation between the samples. Okay. So in this example here, it takes multiple different locations: Tillamook, Newport, Petersburg, Magadan. I'm not sure about the pronunciation. And this one starts with 2 consonants, so I'm going to be in trouble. Tvarmany? I don't know. I'm guessing it's somewhere here on the East Coast, though. And these statistics are the length of the anterior adductor muscle scar, standardized by length for a certain kind of shell that's being found. Okay. And from 5 different locations. So with regard to that, it's just some measurement that's being found on some seashells. And we're going to run this F one way through it. And all we did here was to make lists. It didn't make them into NumPy arrays. That came back to haunt me later. But we can just go ahead and feed them lists. If you got time, experiment and see if you fed it NumPy arrays instead of lists. Would it make a difference? I don't know. So let me know if you find out. But then the thing that it gives you is the F statistic, which is of some value in some things people do. But to us, we're going to look at the p-value. The p-value is 0.00028. So yeah, that's really small. And that means there's a severe difference going on here, even though all these numbers look the same to me. So in order to tell the difference there, the thing I did was to go ahead and turn them into NumPy arrays, because then I could tell each one to calculate the mean. And then I had a bunch of numbers that I couldn't tell apart either. So I told it to sort that NumPy array of the values. And from having them printed out here, I could see there was a gap of about 0.015 between these 2 here, whereas the other gaps were relatively smaller. And so that told me that the Newport, Magadan, and Tillamook measurements were roughly the same, and the Tvarmany and Petersburg were roughly the same, but bigger than those. Okay. So for problem 3 here, the thing I want you to do is to go pick a make of car that doesn't have a lot of models. Okay. The reason for that is that I don't want you to really overwork this, okay? But pick out something that's got 3 or more models of color and read those highway mileages out, okay? And put those into the different arrays. Oh, different lists. You don't have to make arrays this time. Try arrays though, see what happens. And then just feed that into this F one-way function, and it will just read out for you. See what your p-value turns out to be. If your p-value turns out to be not small enough, then that says that the highway mileage is not appreciably different between these different models. And then you're done. If you've got the different models and you've gotten a p-value that's less than 0.05, go ahead and sort them out and see which one seems to be smallest or largest. I wish I knew a quicker way to do that. If you come up with something, let me know, because maybe you want to share it with other people too. So, all right, last thing, chi-squared test for independence. Now, the notion on this is that we've got contingency tables like this. I poked around and just found someplace where in a YouTube video where somebody was showing people how to do something with the package pandas. We'll look at that more next week, okay? But they were doing one of these contingency tables with pandas, and it just showed the number of females whose education was only to primary school, the number of females who went to secondary school, the number of females who went to post-secondary school, and so forth. And then the totals in the columns, or at the ends of the columns, the ends of the rows, okay? And the question is, are the variables about sex and education? We ought to be maybe saying gender instead of sex, but this is just the data I had, okay? So are those independent or are they dependent? So in this case, you might say, well, whether somebody completes more schooling, is that dependent or not upon their sex? And we pretty much know that that is the case for a variety of different situations that happens. But this is saying, does the data we have give statistically significant evidence to show it? It's just an example, okay? So I found an example where this kind of thing was worked out. And somebody had an array that went like this, 10, 10, 20, and 20, 20, 20. And then it does this chi-squared thing with it. And all you have to input is this array in this certain format, okay? And what it essentially does is to make the summaries so you don't put in the totals, okay? But it will figure out those totals that are out along the edges of the contingency table, and then it will construct what it expected if you had those totals and the proportions inside were because of independent variables. And then it will look to see how different those are. If they're not very different, then you'll come back with a large p-value like this. And you'll say, maybe this was different from independent, but it's not strong evidence of it. So this will read out p-value, the test statistic, degrees of freedom, and the expected frequency. Generally, we're interested in the p-value, but if you need the others, it'll get those for you. So, all right. So your problem number 4 is actually to take that contingency table up there and to do this testing for it. I went ahead and did it, and I believe we did find out that we had a small p-value, and therefore the 2 variables, sex and education, were dependent. But The thing I want you to do is actually run the code for that and insert a text block. Tell me what you find out. Sound good? Hopefully. All right. Catch you later. And assuming I can stop the share and